And for that, we're going to build into 3 steps: vibrations, waves, and then an application on sound. We should start with vibrations because vibrations are the sources for waves. So the first idea is just to see, imagine that you have a spring attached to a mass, right? And if you hold it and then you stretch it, let's say, this is the original scenario. So now let's say that you stretch it. So let's put it in here. Now this is stretched. It's going to be the equilibrium position if you wish. So let's carry it on. And now we stretch it. This is an equilibrium because our hand, we could add the force in here, right? We could just write the force. The sum of the forces is going to be the force of my hand pulling minus the force or plus the force elastic. And where the elastic force is going to be, of course, Hooke's law, so we can write it in here. It's going to be minus k delta x, where delta x is the amplitude or the displacement from the equilibrium position. Okay, and now we call typically delta x. For the purpose of this class, however, we're going to redefine this in a second. But what happens is I have my hand that this is an equilibrium, so the sum is equal to 0. There is nothing moving because acceleration is 0 because the forces are balanced. What happens if you make the hand force go to 0? Basically, what happens when you release it? At that point, because the object was in equilibrium, we remove one of the components of the forces, then the equilibrium is broken, and so we expect to see a net force, and so this is not going to be any more equal to 0. In fact, it's going to be different from 0, right? We have broken and the equilibrium, and there's going to be an acceleration. An acceleration, of course, given by the distance or proportional to the distance of the object, right? Because we can just write this thing and say this is minus k delta x, it's equal to mass times acceleration. So the acceleration is going to be proportional to the stiffness of the spring, but also to the amplitude, how much we have to form that. If we release it, of course, then we're going to experience that we're going to observe that there is going to be a force going up because it's a force, the elastic force, which of course produces an acceleration also going up. But one other thing that we need to track for is the velocity of the object. In this case, the velocity is going to be 0. At the beginning, velocity is 0. So we have a force pointing up and an acceleration pointing up. So what happens at the later instant in time? Let's say this is t0. What happens at the next instant? What we're going to observe now at the next instant is because there is a net force going up, the object is going to start accelerating going up. So velocity is going to be increasing in that direction, which means that the object is going to be basically at a different position now. And in here we can observe that in this case, let's make these arrows maybe longer. In this particular scenario, what we're observing now is that the force is going to be again proportional to the displacement, but the force has decreased because now the displacement from the equilibrium position, which is with the dotted line, is smaller. So displacement is smaller, therefore force is going to be smaller. We can just paint a smaller arrow, and then we can say, of course, that the acceleration consequently is going to be also smaller. But now we have to account for velocity. The object has gained velocity, has been accelerating. It's in fact accelerating in that direction. So velocity is going to be pointing upwards in that direction. If we wait for the next instant in time, let's call it t2, what we're going to be observing now is that the object reaches the equilibrium position. In this particular point, the amplitude of displacement is 0. So the force is going to be, the force elastic is going to be 0, and the acceleration is 0. But here's the catch. The object now has a velocity accumulated from the fact that it has been accelerated at non-constant acceleration, certainly, but has been accelerating all the way as it was traveling through here. At this point, velocity is going to be the largest. And we're going to see why that is the largest, because the velocity has been accumulated in here, so obviously that makes sense that it's the largest. We're going to see what happens next. Because the object is at this point, we say there is no net force, therefore the net force is 0, there is no acceleration, the object will not accelerate. And then what's going to happen with the ball? It doesn't stay there because it has accumulated velocity. And this goes back to the idea of inertia, Newton's first law. In the absence of a net force, the object will keep doing whatever it was doing. If it's stationary, it remains stationary. But if it was moving with a constant velocity or with a velocity, it will keep moving with that velocity. So an instant later, what we're going to observe is that, of course, the spring is going to be compressed. And so now we're going to observe a situation where the velocity, the force is going to be acting opposite, and the acceleration also is going to be opposite and negative. And so the velocity is going to start decreasing. So now the velocity is going to decrease. It doesn't go to 0 yet, let's say, it just goes a little bit down. Now what's going to happen the next instant in time? That the object is going to be, let's say, maximum compression. Let's call it in here. So that's kind of not on the scale, so let's make it even more obvious. So let's make that the object is completely compressed in here, right? So there's certain distance. And now we're going to observe is that the force elastic is maximum. It just goes down. The acceleration is going to be also maximum. And the velocity here is going to get to 0. Why? Because it has been decreasing its velocity all the way up to this point. And now you observe that this situation is actually symmetric, and in fact this one is symmetric. That's provided that the amplitude here, the change in displacement, is the same. And so we observe this situation. Now we're going to have this scenario which again is symmetric to this one. So I can take the entire thing and copy paste, so to speak, and invert it, and what I'm observing at next instant in time is that the object is going to go in this direction. So the next instant in time, because the force and the acceleration go this way, velocity is going to be increasing, but it's going to be increasing, it's going to be pointing downwards. And as it goes here, it is still increasing, but now it's going to be increasing less to the point it reaches the minimum, this equilibrium position where velocity is going to be maximum and pointing downwards. And so it's going to keep going back, and then it's going to go forth and back and forth. So the spring is going to keep going back and forth, back and forth. And this back and forth motion we call a vibration. In the context of physics 2053, we're going to say the vibrations or oscillations are in fact the same thing. We're just describing it with the same different words, but they are basically the same idea, which is a motion back and forth around an equilibrium position. This position is the equilibrium position. Because if we had this object starting from this point, it will always remain in that point. So it's always moving around this point. Now, if you remember at the beginning of this course, we said there were two types of motion. One was translational and one was rotational. Then we introduced the idea of heat, and we said in solids, heat is actually a temperature which is proportional to the average kinetic energy of the particles. It's actually proportional only because particles do not much rotate to translate. It's pretty much vibration. And we never discussed vibration. Vibration is always motion back and forth around an equilibrium position. All this motion is happening around this point, which is the equilibrium position. So that's what we describe as a vibration. Now, vibrations typically can be when the vibration, let's say, repeats itself because the object goes completely back to the same position. We said that that vibration is periodic, right? So back and forth, we say this is a vibration, which, so to speak, would be a third type of motion. In reality, you could always say that this is translating back and forth, but we're interested in defining this new category because it always happens around the same equilibrium position or around the same point. Whereas in a translation, you're free to move, right? The translation would be the ball going here, there, and then there. But now this one is actually just moving around an equilibrium position. If the vibration repeats itself, we call that, because it's repeating itself, then we say that that vibration is periodic, okay? Now, how do we understand this idea in terms of energy and this idea of repetition? It makes more sense if we do it, from an energy point of view. This is going to be T2, and then of course this is time 3, and this is time 4, okay? So what we observe in here is that we have two sources of energy. One is going to be potential elastic, and one is going to be kinetic. And in this case, kinetic means the velocity of the particle, so of course it's going to be 1/2 k delta x, remember, and this is 1/2 mass velocity squared, okay? This is the definition of potential elastic and the definition of kinetic. Now, what's important in here is we can observe in every instant in time how is the balance of energy going, and that's going to help us understand how this motion occurs. At the very first point, we have no kinetic energy, and we're going to have maximum potential elastic because the object has the maximum stretch. If we call psi sub 0 the amplitude, right, say the deformation, the maximum deformation, we're going to have that the potential energy here is going to be potential, let's say, proportional to this. We use psi because it doesn't need to be vertical. And this motion, you might be thinking, where's gravity? Because you're seeing it vertical, but you can imagine this happens on a table, so there's no weight involved in this direction, okay? Okay, so that's going to be the energy in here. In this case over here, we have no deformation, so potential elastic is going to be 0, and all the energy is going to become kinetic. So this is going to be the case where we go from full potential to full kinetic. And what happens in between is that we're going to have a little bit of potential, where now it's not psi sub 0 because it's not the maximum, but just a different deformation, and a little bit of kinetic that we could call V prime, if you want to say that this is not the same as that one, okay? So what we're observing, if we plot like a sort of diagram, what we're observing here is that first we have full potential and 0 kinetic. And as time happens in here, we're going to find the opposite situation. Now we have 0 potential because it's not the form, but we have maximum kinetic. And this point in between, of course, is going to be like half and half, so or whatever, right? But just basically the idea here. And the idea here is that the total amount of kinetic and potential energy goes a little bit to kinetic and goes completely to kinetic. And then it's going to repeat itself, but going in the other way, right? So this case is going to be half and half again. And finally, we reach the situation, reach again the situation where we have full potential and no kinetic energy. Why is this important? Why is it interesting to see it from the accounting of energy? Because we see that the potential energy here and here are the same, which means that this psi sub 0 is going to be the same psi sub 0 in here. So this one is going to be the same as that one. The amplitude is constant. And this is going to be showing us that an object where there is no loss of energy, in this vibration, in this oscillation, all the energy is going to be going back from potential to elastic, again from kinetic to elastic to potential, and then again from potential to kinetic, kinetic to potential, potential to kinetic, and so forth. So this balance is going to be going all the way. And if you see this motion, of course, you're reminded of a pendulum motion. And pendulum, in a way, is actually the same thing. We're going to have a pendulum that has two maximum positions, and then a position over here where kinetic energy here is maximum, here potential potential energy, in this case is gravitational, becomes maximum. And this is going to be symmetric with respect to this point. So pendulum also offers another approach to this vibration. There are 2 or 3 parameters that we can introduce in the cases of vibrations, and also accounting for energy. From the accounting of energy, we're going to see that if there are no losses, for instance, there's no friction, if this object is on the table and we don't have friction from the table, then all potential is going to become kinetic, there's no loss, because there's no change in energy, because there's no external forces doing work on the system, or the system is not doing work on anything else, right? So conservation of energy, energy needs to be conserved, right? So we say energy is work, but if there's no external forces, that means that there is conserved energy, right? Now, if we had friction, for instance, then we had a problem, because then some of the energy is going to be lost. And what we're going to be observing is that as we advance in time, the oscillation becomes every time smaller and smaller and smaller. Why is that? Because the entire energy of the wave, in reality, or let's say the total energy of this vibration, is going to be proportional to the amplitude of the original displacement. This motion doesn't start from here. It always starts from a situation where you have potential elastic, you release it, and then it starts vibrating. If it was here and you release it, it's going to remain there. So you put energy, so to speak, into the vibration by deforming this spring mass system. By deforming the spring applies the force that is going to be responsible. And that force and that energy is going to be proportional to the square of the amplitude, very important, to the square of the amplitude, not just to the amplitude, to the square, which means that if I deform twice as much, I'm going to have 4 times the energy of that vibration. So before we were introducing the idea of energy vibrating, and we're going to have kinetic energy, and we're going to have we said kinetic energy in the case of heat is going to be translational, rotational, or vibrational in general. In the case of solids, mostly is vibrational. Well, this is this idea. We can think of that this is maybe, I don't know if this was, let's say, you can use this basically. The idea here is that any oscillation that you have of this sort, when it's periodic, we call many times harmonic oscillator, when it has this sort of dependency and it's proportional to the deformation, as we're seeing. And the idea here is that this same mathematics, which again we're not introducing, we're just seeing the concept in here, is actually very interesting because it's used in a lot of different applications in physics. For instance, in developing Lorentz, to the Lorentz model, which is beyond the scope of this and any other courses probably you're going to be taking, is the description of how electrons, follow external electromagnetic waves coming to them, right? So, in other words, how matter or metals in particular react to, and dielectrics react to external sources or external waves. We use also this sort of modeling. And so we also use it for this. We can use it, as we say, for vibration, which accounts for thermal heat. You can use it also to describe, although the pendulum has certain specificities, but basically it is mathematically the same thing. And the idea of this vibration, of course, is that once you solve the mathematics for this, there are many models, many things in physics that can be modeled in a first approximation as this sort of vibration, where the vibration energy is going to be proportional to the amplitude. And again, there's a myriad of applications. You can think, for instance, of an object floating that you push it down and how it goes up and down floating because of buoyancy. It's another example of that sort of situation, right? So this sort of back and forth motions, we call them vibrations or oscillations. When they're periodic and of this mathematical form, you can have hear many times that this is called a harmonic oscillator, okay? Without getting many more details, which would require differential calculus, which of course we are not considering in Physics 2053. This is basically the idea. Now there's a couple of things in here that we can describe is how long does it take for the pendulum to make an entire cycle. And cycle means go up and go down. One cycle we call, the time it takes we call the period. And then this reminds you of the angular motion we were saying, right? So we can describe period as t, which is the time it takes for one cycle. And the other thing that we can describe here is psi, which we can say is the amplitude. And of course, if we have an amplitude, psi sub 0 is going to be the amplitude. So this describes pretty much the oscillation, because the energy comes from amplitude, and how fast it does this thing comes from the period. We can mathematically, we're not describing that, we're not deducing that, but we're going to introduce mathematically what is the period for a spring mass object, and also what is the period for the pendulum, because those are two questions that are interesting to see, and we're going to use in the problems. So let's see that. So let's study some parameters of the oscillations or vibrations. To begin with, one of the things we can realize is that we can plot in time, so to speak, if you wish, in time, how much is the deformation of the spring. And again, remember, you start the stretching and you let it go. So what you observe is that with respect to the equilibrium position, that we can call it, well, actually we can just call this 0, then we don't need that. So the equilibrium position is going to be here, right, which corresponds to the point where delta x is equal to 0. Basically, it's in equilibrium, the spring is in equilibrium. So we can observe that the beginning is maximum, at a certain time it reduces, then it gets to 0, then it goes halfway, then maximum again, and then again, let's say, it does this sort of thing. So if you join the points, you can see that it does something like this, right? So something maybe like this. And if you just keep observing, because the motion goes back and forth, what we're going to be observing is that this follows this sort of sinusoidal thing. When we're plotting it in time, the distance it takes for an object to go back and forth, that's what we call the period. Now, instead of defining the period, we sometimes use another variable which is called frequency. Frequency is, as the name says, how often something happens. So how often is going to be used in hertz, typically, which is inverse second. And the idea here is that frequency f is just going to simply the inverse of the period. When the period is short, it's much more frequent. If an object comes, if the bus comes every 10 minutes, it is much more frequent than if the bus takes 1 hour to take the entire run. Because if it takes 10 minutes, every 10 minutes the object comes. So this number is going to be smaller, it's more frequent, frequency is larger. Whereas if it takes 1 hour, this is going to be larger, therefore this number is going to be smaller. So this is something that we use now, we see mathematically, it's just simply the inverse of the period. Now, one of the ideas in here is, of course, you're going to see sometimes we're going to have systems like, as we say, that there is spring mass like, and we call that harmonic oscillator or simple harmonic oscillator, right? And here the period is just simply given, and again, we will not describe this, but the period is given as 2 pi times the square root of the mass divided by the spring constant. And this is the mass of the object. Now we can intuitively understand this. Now mass, again, remember, is the inertia. So how lazy an object is, because inertia again is laziness. So how lazy an object is proportional to the mass. The more massive, the more lazy. Lazy meaning it opposes most the change in its motion. And a period is constantly, in a vibrational motion, you're constantly accelerating, right? And you're in fact accelerating with different accelerations. It's non-constant acceleration. So what we're going to observing is that the mass is going to be very important. It's going to be relevant, because an object that is very massive, it is much more lazy. So it takes a longer time to do an entire cycle, to go back and forth, which is what we're plotting in here, go back and forth. So that takes much more longer. So the period, of course, is proportional to the mass. The more massive, the more inertia, which takes more time to do the same thing. And it's inversely proportional to the spring constant, because the more stiff it is, the less stiff it is, it just takes less. When the more stiff it is, the force, elastic force, which is the restorative force, is going to be proportionally increasing, and therefore the acceleration is going to be increasing, so it's going to be changing velocity faster, and because it changes velocity faster, of course, it's going to be just increasing, it's going to be decreasing the amount of time it takes, right? Well, the amount of time it takes is the same if it's periodic. What I mean here is, like, if you take two systems with two springs, the same mass, but one spring is twice or 4 times as stiff as the other one, is going to take half of the period of the other, right? You can make the numbers in there. But this makes sense. the more the force is proportional to this, so the more force that we have is going to produce more acceleration, so acceleration is the change in velocity in time, therefore it's going to be changing its velocity in time much faster, and so it's going to be taking less time to actually do one entire cycle. In the case of a pendulum, it's also interesting to describe that equation. In the case of the pendulum, the period is actually going to given by 2 pi, and the period is going to be L divided by G. Couple of things in here. The period of a pendulum is proportional to the length and of course to the planet in you live. And this simple equation is actually going to provide you a way to calculate what is the gravitational acceleration, 9.8 or 10 we have been using for simplicity, of Earth on the surface. Take a pendulum, let's say of 1 meter, stick, then count, let's say 10 oscillations, and then you can figure out, just tend to average the error, okay? And then you can figure out what is the gravitational acceleration from that, right? So this is a nice thing to measure gravitational acceleration. You just simply can take a pendulum, and historically this has been done also to go up in the mountain and see, hey, how much does this change with height, for instance. That will be a way. The idea here anyway is the pendulum just depends on the length. Important thing, does this depend on the mass? It does not. There is no mass anywhere in here, okay? So it does not depend on the mass. So if you take a pendulum and you take a pendulum with this mass and you take a pendulum with this mass, right? Both take, if the length is the same, both take the same time to do the oscillation, the same. The only thing that changes the oscillation is the length and of course the gravitational acceleration. Something on the moon would be going slower than something on Earth, oscillating, a pendulum of course, okay? It does not depend on that. And something important for this, does amplitude play any role? It does not. The amplitude of the motion, the amplitude which gives, the amplitude just relates to energy. The energy of the vibration is proportional to the amplitude, but it is the period, it is not proportional to the amplitude. There is no amplitude in here, there is no amplitude in here, which means that the time it takes for the pendulum to do this motion is the same as the time it takes for a pendulum from here, let's say, to go to there. It takes exactly the same amount of time if the length is the same. And always there's an assumption here that you never go very high in the deformation. That's why it's usually called simple pendulum and in a first approximation. Or you can have also composed pendulums where there's a pendulum attached to another pendulum and things like that. Okay, but that's much more advanced. We don't care about that. Simple pendulum, small amplitude, then you can make an approximation where you actually get this equation, right? This is the equation that there is very small angles, and so the sine of the angle is going to be equal to the angle itself, and that's how we derive this. Again, it's not content for this course to describe how this is obtained. Let's take it as a given in this case and keep working. Physics 2048 is going to be describing exactly how you obtain these equations, but again, you need differential calculus, or you just use some arguments, which I'm not really a fan of, but you can find them in textbooks anyways, okay? But important ideas here, pendulum depends only on the length and on gravitational acceleration. The harmonic period depends only on the mass and the spring constant. Of course, if you have a system that is not exactly a spring constant and a mass, you're going to have to model that as spring and a mass. So you have to identify what is the mass, and you have to identify what is the spring constant. If we were talking about the object going up and down in water, for instance, in buoyancy, something oscillating in there, then we have to determine, or we could determine what would be the equivalent spring constant of that system, right? But of course, there's no spring constant in that system because there's no spring. But this is just in the point of view of vibrations. So vibrations, when they're periodic, they're described by a period, and they're also given by an amplitude. The amplitude is the distance from the equilibrium position to the maximum deformation, and it is the same whether you go up or down. The only thing that the only time where this is not fulfilled is if there are losses of energy. If there are no losses of energy, the same energy needs to be here, 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 and there. And because here and here there is no kinetic energy, it's fully potential, then the same potential is in here and there. And because potential energy is equal to 1/2 of the spring constant times, right? The potential energy, we said it's equal to 1/2 of k delta x squared. If we say that this is the same spring and it's the same potential energy, then this needs to be exactly the same. The only thing that changes is that you go positive or negative, but because it's a square, that sign goes and disappears. And so the same potential energy is in here and there, therefore the amplitude is the same in there, in there. Now let's see what happens when we take vibrations and we propagate them in space, which is to say when we have waves. So what do we call a wave? A wave is a perturbation or a vibration or an oscillation that propagates in space. So let's say it's a vibration that propagates in space. What is the idea here? Say that you have a system of atoms, a chain of atoms in a solid, let's say, and let's say it's one-dimensional. all of these atoms are connected, let's say, by a spring. It's not the same spring that we're talking about. This is just simply a spring that, or some sort of solid bar, if you wish, right? That this is the interaction force. They're bound together. What happens if I pull this one up? Well, if I pull this one up, because they're connected, the other one is also trying to go up. So what's going to happen is that I'm going to find something like this. Right? If I bring this up, what I observe is this goes up also as a result of that, because they are interacting, they're joined together. So what happens is if I bring this one down, as I bring it down, we recover the same situation, let's say. Let's say something like this, and as I bring it down again, we can observe the same thing, basically, kind of, and this, right? So we observe what's happening. I'm only handling this one, and this is the one I'm moving up and down. But as a result of that, this one is going to be also moving. And so if I do this deformation and high enough, what I'm going to observe is that I bring this one and down, this pushes this one, and it's going to bring this one. So what's also going to happen, if I do this, is of course that I'm going to observe that this one moves up and down, makes this one also up and down, which also in its part is going to be moving this one up and down, and this one is going to be pulling up and down, and so forth and so on. And so this is equivalent as if I take, for instance, so that's you have some dominoes arranged together, right? And then you push this one, and then you have what we call the domino effect, right? So if I push this one, I am only pushing this one, but this one pushes the other one, that pushes the next one, that pushes the next one, and then pushes the next one. And now I'm asking you, is any of these dominoes moving? Well, they're actually moving, but they're moving with respect to the equilibrium position, which is where they are. So there's no net motion of the dominoes. What is moving, actually, what is being transmitted is the vibration. So that we have is a wave. In this case, would be, let's say, a pulse, right? Because we're taking a vibration and we're propagating in space because things are connected. This is basically the idea of a wave, and it's very important to remember the waves at the end are, this is waves, right? So these are waves. And if you remember this thing, there's many things that are going to be obvious for waves. So to begin with, as let's say you move down, yeah, anyway, this is just the first approximation. If we keep doing that and we do the not amplitude, then we're going to start seeing that this pulls from that one, and then we're going to start to see that these ones follow suit, and then eventually that thing propagates. So important thing here, however, as I move this up and down, the other ones are moving, although I'm only moving this one, I'm only vibrating this one. This is a vibrational motion, but this is also going to be a vibrational motion, this is a vibrational motion, this is a vibrational motion. So none of these atoms is traveling. None of these atoms are traveling, excuse me. What is actually traveling is not that, what is traveling is the vibration. And what is the vibration? Vibration is just that motion back and forth. So what's actually traveling is not the material. Matter doesn't travel, right? So matter does not travel. Waves carry the vibration. And what is that vibration? Well, that vibration is just the energy, which is the motion I put. And because the vibration is the one that's moving, and the vibration is motion, and that motion is defined or described with certain energy, what I can say is that waves carry energy. And this is a very important distinction, because this introduces a completely different phenomena that we have not covered in the entire course. That's why we took it to the end, way to the end to actually introduce it. And this is the idea of waves. In physics, so far, we have assumed that everything, whether it's a solid, it's a liquid, or it's a gas, everything eventually is just moving around. And by moving, we mean that there is matter displacing from one side to the other. This is the first time we're going to be seeing that there is motion happening, and the motion doesn't happen because matter is moving, but rather because the energy is moving. And if we are capable of appreciating that the subtlety, then there's many things that come after. When we observe, for instance, electromagnetic waves in physics 2 or physics 2054, which are not going to be that weird. For instance, we're going to see that waves, electromagnetic waves, carry energy. Sound waves carry energy. The waves of, obviously, you know that, the waves of the sea carry energy, but they don't carry water. They're just moving the energy with the water, okay? So that's an important distinction to make, and so we're understanding that we can use waves as a different description of motion. So we're going to have motion of particles, and we're going to have motion of waves. And this, everything pretty much in physics is going to be described as, is it moving as a particle or is it moving as a wave? And then we're going to have all this quantum duality of the wave corpuscle approximation, whether light is corpuscles or whether light is wave, and so forth. There are things here to describe. Important ideas in here, however, that we want to have for waves is the waves are vibrations that propagates in space. This is important idea. So what's going to be the energy that the wave carries? The energy is going to be the energy that you put in the vibration, because that energy is the one that's going to be carried on. So what is the energy of a wave? The energy of a wave is going to be proportional as well to the amplitude, which in this case, we say is going to be proportional to the amplitude of the wave. And the amplitude squared, right? That's the amplitude. So the wave energy is going to be proportional to the amplitude. Other ideas that we can discuss in here, there's no net matter motion, there is only wave. Now there's an important thing. Before we said let's analyze a single point and let's see how it vibrates in time. In waves we can do something similar, but because now they propagate in space, what we can do is say let's observe a single instant in time. So first we said before for vibrations, we said we fix position and observe time. And what we could do is just plot the disturbation or the perturbation or the vibration or oscillation and see how it goes in time, and we said it goes like this. And this is in time, how it travels in time for a given point, right? And so I observed that this goes like that, and we define the amplitude, and then we define the peak-to-peak distance as the period, right? Now we can do something similar but the opposite. We're going to say we're going to fix time, and now we're going to observe space, x. And that will be just to take a snapshot. Instead of fixing here and see how it goes in time, now we're going to take the entire thing, which is just taking the entire space, and we're going to fix in time. We're going to take a snapshot. And if we do that, what we observe for a wave as it travels, it also is going to be describing, let's say, something like this. In space, now this is a space, now this is not time, now this is a space, okay? And what's important in here then is that we can observe that this is exactly the same, this is still the amplitude, but now we have a distance of crest to crest, which is the maximum position, which is another way. If these were atoms, this atom is up, so what we are observing is that this atom is the form there, then we have this atom here and this atom here, maybe this atom there and there and there, and so we have all this, these will be atoms, right? Let's say that are moving up and down. Okay, so distance, how far away in space, because we're observing a space for a given amount of time, is the next peak, which is exactly, this atom is doing exactly the same motion as this one, and that we call wavelength or lambda. And the idea of the wavelength is basically the same idea as the period, but now we're talking about the period in space, not a period in time. So we don't have a temporal period as we're used to. Now we can define the analogus of that in space, and then we say we have a spatial period, and that spatial period is what we call the wavelength, right? Wavelength is typically denoted by Greek lambda letter, which is lowercase l. Okay, so this is the idea for amplitude in waves. Waves can be described by period and amplitude, which is for the vibration, but they also need to be described on how much they spread in space, which is another way of saying how much they vary in space, which is another way of saying how much is their period in space. And that's what lambda or wavelength gives you. Now, last thing to say in here, we have been assuming that the vibration goes like this, but in waves, there's two types of vibrations that we can observe. Sometimes waves are going to be vibrating, or the vibration that generates the waves is going to happen in the same direction as the energy motion, and sometimes it's going to be transversal. So when it's transversal, this is better observed by, let's say that you're here and then you are grabbing a string and then you go up and down, and what you observe is that the spring goes like this. And so the wave travels in this direction. The vibration happens in this direction, but the wave travels in that direction. So this one and this one are transversal, they're perpendicular. And so we call that transversal waves. There is another scenario, which we saw in class, where the perturbation or the vibration doesn't happen perpendicular to the motion of the wave, but it actually happens in the direction of the wave. And that's better explained, for instance, with the slinky, right, which is a spring, and then you quickly go and stretch and push, stretch and push. And what happens is you're going to be observing that these things compress at some areas, expand at others, compress and expand. And that thing is going to be propagating. But if you see the direction of propagation and the direction of the amplitude deformation, it's actually happening, or the deformation, the perturbation is happening in the same direction. And so we call those longitudinal. And it's going to be important because in the next one we're going to see what happens in longitudinal waves, in a particular case of those, which is sound, because electromagnetic waves are going to be transversal. Transversal waves and longitudinal waves have certain distinctions that we will see. What we're interested in here is just to introduce this distinction. Because the waves are carrying energy and energy is traveling, we can say that the velocity of the wave, that's the last thing we're going to say for waves, the velocity of the wave is how much it covers in a given time. So the best way to characterize probably is going to be saying it travels a distance lambda in a time t. And so we can say that that's actually lambda times frequency because the period is the inverse of the frequency. So any wave has this relationship between the velocity of the wave and the wavelength and the frequency of that wave. This relationship, which is going to be important for the problems. Last thing to say in here, the velocity of the wave depends typically on the parameters of the material properties, right? It does not depend on the vibration. And why is that so? Because the vibration is going to change depending on the material, whether because it's atoms and we're taking the spring-like, different atoms are going to have different mass, and different atoms are going to be interacting differently, and so they're going to be changing their period, as we saw before, and so we're going to see this is going to change, so the velocity is going to also change, right? And we can see different things in here. The energy of the wave is going to be still proportional to the amplitude, the velocity is going to be given by this sort of relationship. But the velocity of the wave is independent of, it's just dependent, on the material properties, okay? So how fast the wave travels, it depends on the material, period, okay? So that's going to be an important thing that we to bear in mind. This just completes, let's see, some, the description of waves, which are perturbations, vibrations, oscillations that propagate in space. Important idea, waves do not carry matter, they carry energy, and this is going to be interesting because this is a different approach of physics or a different phenomena in physics where we have motion. That's why we carry energy. Energy is motion, right? Remember, we introduce energy as accounting for motion. Well, there's an amount of motion available, and we can move that amount of motion through waves. And we will see that in the case of sound. You can see it in the case of light. There's many other examples of that scenario. But there's just very basic parameters that are going to be useful, hopefully, for you when you go to Physics 2 and start analyzing electromagnetic waves and light. So in problem number 1, we have a spring attached to a mass, which we don't know, that it's oscillating with a frequency equal to 0.83 hertz. And remember that hertz is the same as the inverse of a second, okay? Then we're going to add another mass to that, and so we're going to have a scenario 2. And in the scenario 2, we're going to observe is that the mass now, the mass has now an extra mass, if you wish, so it's m2 and m1. And now when you do this, there's a different frequency, which is 0.6 hertz. Correct. And so the question is, what is mass 1? Because we know that when we add mass 2 is 0.78 kilograms, right? So the question is, what's mass 1? Okay, what relates this spring and that spring, or what information we have is basically we have the frequency, and we remember the frequency is the inverse of the period. So what we can observe is that the T1 is going to be basically the inverse of the frequency 1, right? And so it's going to be 1 over F1, and that we know is 2 pi square root of the mass 1 divided by k. And now similar, we're going to do the same thing for T2, and now it's going to be F2, which is equal to 2 pi of the mass, but now mass is m1 plus m2, because it's not just simply mass 2, it's mass 1 and plus 2, and that's divided by the spring constant. What can we do over here? Well, what we can do in here is just take, basically solve for mass, for instance, in here, and we can observe that, let's write this thing down. So 1 over F1, it's equal to 2 pi square root of mass 1k. If we try to solve for mass 1, what we're going to do is 1 divided by 2 pi F1, it's equal to square root of mk. So what we can do is everything squared, and so we're going to find that 2 pi F1 squared, it's equal to mass 1k. And so that tells us that k divided by 2 pi squared times 1 F1 squared, it's equal to mass 1. This is the first realization. Now we can come back then here and solve for, but we don't know k, right? So we know F1, which is 0.83. We know 2 and pi, of course, but we don't know k because it's constant. So that's why we had to add another system. So we can do something similar for the other one. Now instead of going let's go step by step. But basically something that you could do simply is that this is the mass of the spring. And so we have solved the mass of the spring as a function of the frequency of the spring, like spring constant, So which means that any other system I can rewrite directly. So I could just simply say that m1 and m2, which is the total mass in this new system, is going to be the same as 1f2 squared times k divided by 2 pi squared, right? You can solve this yourself, but we have done all the effort already ourselves, because that's going to be the same thing here. Now m1 plus m2, it's m1, because it's the total mass of this system. And so simply that's just allowing you to do that. And what we know now, or we can do now, excuse me, is just to realize that if we take k to pi squared, we have k to pi squared in both sides. So basically we have these two equations. But this and this is the same in both equations. So what I can say then is just solve for, let's say, k over 2 pi squared, and so what I observe is k over 2 pi squared, it's equal to m1 plus m2 times f2 squared, and over here, so let's write it down. What I can observe is that k over 2 pi squared is equal to m1 plus m2 times f2 squared, but it is also equal to m1 f1 squared. And from here then we can just say that we have f2 squared m1 plus f2 squared m2, it's equal to m1 f1 squared. We can just move that thing, let's say, here, and so we find that f2 squared m2, it's equal to m1 times f1 squared minus f2 squared. And so we can just take that thing divided and finally solve for m1 and say that that's f2 squared divided by f1 squared minus f2 squared times the mass 2. And if we add the numbers in here, we can just say that this is f2 squared is going to be, f2 is this thing, f1 is this thing, and m2 is this thing. So we have all the information actually required. If you run the numbers, what you're going to find is that the solution is 0.85 kilograms. And this is a nice example because it allows you to determine the mass of a spring based, if you knew the spring constant directly, you can derive the mass because we would go here. But because we don't know the spring constant, something clever to do is add an extra mass that you know. And if you know that extra mass, you know how to adjust this equation, and then finally you find the solution. So it's a nice way of calibrating, for instance, or measuring the weight of an object is by using a spring attached to a mass and making a vibration and calculating what's the spring of that system. And so from that period measurement, you can actually determine the mass of an object. So that's pretty amazing, right? That just follows from the fact, as we said, that the period of a mass of a spring mass-like system is just it's proportional to the mass, or the square root of the mass, and inversely proportional to the square root of the spring. So if I keep the same spring, that doesn't really add anything. Most of the proportionality of the difference is going to be the difference between the frequencies, of course, difference to the masses. And so that's basically what we're making use of in here. But again, we said pendulums can be used to measure gravitational acceleration. Now we see pendulums can also be, springs could be used to measure mass. Interestingly, however, you could not use a pendulum to measure the mass, because the period because the period does not depend on the mass. But a spring-like system does, the period depends on the mass, and so we can use a spring-like system to measure or determine the mass of an object, an unknown mass of an object, if you know the spring-like, but even without, which is the clever idea that these guys had in this experiment, right? Let's add a new mass that we know, so we do not rely anymore on the spring constant. That's the same for both systems. That can get out of the equation. And eventually just make some arithmetics and just find this result. Problem number 3 in discussion says there is a mass of 200 grams oscillating, which of course we can directly write in international system, that oscillates in a frictionless surface at a frequency of 2.5 hertz, right? It's going back in 2.5 times per second, right? Means in 2 seconds it will make 5 cycles. That's the idea of a frequency inverse of the period. And this is doing so with an amplitude. I'm going to use the psi character as we discussed to describe the amplitude, not to confuse them with area, that we use A in pressure, for instance, we said force over area, and we use A. So just to avoid that, we can call the perturbation or the distortion, the amplitude of the perturbation psi sub 0, right? Psi is the same letter for psychology, right? Psychiatry and all those things. So, and it says that the amplitude is 4.5 centimeters. So of course we can write this the same way. We could just always say this is 4.5 10 to the minus 2 meters just to be an international system. And the question is, what is the effective spring constant of this motion, right? Because there is this is a spring attached to a mass, right? So we said it's a spring maybe attached to the mass, and then this is oscillating on the table, but there is no friction, so we don't have to account for the fact that these are damped oscillations because energy is not being lost, right? Remember that we said oscillations could be natural oscillations where there's no losses, free oscillations we call this. This is a free oscillation because there is no loss of energy. But if there was some loss of energy, for instance, if there was friction and the mass was actually touching the surface, there will be some friction acting all the time, and so the energy will be lowering, right? So if we say that this is the perturbation amplitude in time, in the case of a free oscillation, we go from maximum to minimum, and so forth, right? We call this free oscillation, where this is the amplitude, which is of course the same as this one for the discussion we just made. Now, if there was friction, right, we would have what we call damped oscillations. And the idea there is that we have an initial potential energy that becomes kinetic, and then again potential, and then kinetic. But in between, there is a force acting, or the system is doing a force out of the system, so the system is doing work, right? It's extracting, something is extracting energy, in this case could be friction, and we're going to observe is because you're losing energy, the maximum energy, you go from potential to kinetic, kinetic to potential, but at that time the potential is not anymore the same potential as the beginning. Actually, it's less because there's less energy. We're extracting energy all the time. So what is going to be observed is something like maybe something like this, where you see the oscillations get damped and eventually go to zero. And this is what we call damped oscillation because the oscillation is losing the energy, for instance, because there is friction, right? We can write here friction, right, for instance. And there's the last option, which is the idea of forced oscillations. And we'll get to that again, but the idea of the forced oscillation is that the oscillation of the system is not the proper or not the natural, as we call the natural frequency of the system, but rather is going to be given by the force of someone. And that would be like, let's say that someone was grabbing the spring, right, and moving it back and forth. If you take the spring and you move it yourself back and forth, the spring is, of course, going to be running with the frequency which you impart to the system. It's not going to be anymore the frequency of the system itself left to its own, which we call natural frequency, but it's going to be a forced frequency. And in that case, the amplitude and everything is also going to be related. The amplitude and the frequency are going to be related to this. So potentially in the same spring mass system that we have in here, instead of having this, in this case, this period, right, we could have a different period because the frequency could be different. For instance, you could be running it like this, like going very fast, right? And so that's going to be a forced oscillation. So now the frequency, which is this thing, it changes. The period now has changed because now it's being driven, right? So this is the idea of the different examples, free oscillation, damped oscillation, forced oscillation. You can see this, for instance, if you think about a child on a swing, and then you let the child do its own thing, and this is free oscillation. If the child, for instance, touches the ground with his feet, he's losing energy because of friction every time that he goes down. Let's say that this is the swing. Every time that the child goes down, if he touches the surface here, there is some friction, so he's losing some energy. And so eventually he's going to be reducing, he's going to go back and forth, and every time less and less until he just disappears. And the last example, which is the forced oscillation, we could just imagine maybe the child is being pushed by his dad or something, and so we're going to have that the child now is going to be following a different frequency, right, which is going to be given by the father. And from here comes that idea of resonance, which is the idea that if you are driving it with a forced frequency that we could call prime, and the forced period, which from here, let's say the forced period, we get a forced frequency. From this we have the natural, sometimes called to T sub 0, and we could call F sub 0, which we call natural frequency, right? And this is the forced frequency. What we observe sometimes, what we observe is that if F prime gets approximately the same as F sub 0, we have the phenomena which is called resonance. And every time you hear about resonance, it's because the systems themselves always have a natural frequency, because they are oscillating systems. And from that, left to their own devices, so to speak, in free oscillation, they have a frequency. Now, if you were running the system with a forced oscillation, and that the system is going to be running with the oscillation of the force that makes that. In this case, it's that pushing. So how frequently that push is going to be running the system, right? And eventually, if you run the system at the same frequency as the free oscillation, what you can find is what we call resonance frequency. And this idea is that you're also putting energy, but every time that you apply a force in a force oscillation, you're doing work on the system, so you're putting energy, right? Depends on how you do it, in phase, out of phase. You could be considering that you're extracting or you're putting energy, or you're doing nothing. But if you go approximately about the same frequency, what you find is resonance. And this is the idea, for instance, and what happens in resonance is that the amplitude goes, mathematically would go to infinite. We cannot see that in physics 2053. You would see this in calculus physics 2048, but it is that you can find that this is a singularity, and so the system would require an infinite amplitude, and that of course would mean an infinite energy, which of course in real systems that doesn't happen because nothing has infinite energy. But the idea is that of course the amplitude is going to be so large that the system can actually break. And this is, for instance, the example of the opera singer who takes a glass and she starts singing, and her voice is going to be acting now, or the waves emitted by her voice is going to be acting as the forcing frequency. If you take a glass, you wet your finger and do that thing, sometimes you hear the sound, right? That sound is the natural frequency of the glass. Now, if you were to do that frequency with your mouth, you can couple your mouth to the cup, and you're doing it at a force frequency, which is approximately the same as that one. And what happens in that case? The glass shatters. Why? Because the glass starts to deform with the largest amplitude, and that largest amplitude is too much for the glass, and the glass breaks. So this is just the idea of difference between free oscillations, static oscillations, and forced oscillations that we saw. Now, in this case, we have free oscillations because there are no losses in friction and because there's nobody driving the system. And most of the cases that we're going to see in physics 23, is going to be always free oscillation because it's much more easier to see anyways. And so in the question in here, we are given all this information, and we're being asked what is the spring constant of this motion. And this is an interesting thing. Every time that you have a back and forth motion, which we call this an oscillation, a vibration, or a perturbation, and it's proportional to the amplitude of that, the period is proportional to the amplitude of that, we're going to be talking about a harmonic oscillator, right? Which is a spring mass-like system. So from the frequency of that frequency, if you know the mass, you can actually describe the effective spring constant. In this case, the spring constant is just the stiffness of the spring itself. But you could try to model many different systems, as we discussed, with this harmonic oscillator idea. Not just simply a spring mass system, but maybe other systems. Maybe you can think about a floating device that you push it down and goes up and then goes down and goes up and something like that, right? So that sort of device would also be, you could potentially describe it as a spring mass-like system or a harmonic oscillator, and in that case, then you can still apply the equations that we apply for a spring mass system, which says in this case that the period is equal to 2 pi times the square root of the mass divided by the spring constant, correct? And so in this case, you will be talking about effective spring constant because there is no spring as such, right? Every time that you make an analogy between a system and a harmonic oscillator, which at the bottom is like a spring-like system, we're going to be talking about effective spring constant, which is how stiff the system is. It's just another way of characterizing that oscillation through the stiffness. And in this case, we're asked to figure out what is the effective spring constant for this motion, and of course we have the frequency, which means that the period, which is the inverse of the frequency, is going to be 1 divided by 2.5, and that's going to be 10 divided by 25. That's 1/4, right? 100 divided by 25 is 4. So that's going to be 0.4, right? .4. So in that case, 0.4 seconds. So the period that we have for this frequency is 0.4 seconds. Now from here, then we can try to figure out this one because we have the mass, we have the period, and we're trying to find that one. So what we're going to say is that the k it's equal to, we can just go step by step, but basically it's going to be t squared divided by 2 pi squared. Sorry, let's put everything into square. It's equal to mass divided by k, which is this, and then what you're going to say is that k it's equal to mass 2 pi divided by period squared, which you might see later on that 2 pi over t is angular frequency, and so that's going to be m double n omega squared, which is the spring constant anyway. Okay, so from here we can replace the numbers, and so we have is that the mass is 0.24, the period, the 2 pi is 2 pi, of course, the period is 0.4 seconds, and then we make this square, and so we make the math. It's about 59 newtons per meter. And so we found what is the constant, the spring constant of this system, just basically based on analyzing what is the mass and what is the frequency. excuse me, the frequency of the oscillation. Let's erase this and do part B, which is about energy. So part B says how much energy is involved in this motion. Remember, we said the energy, just to remember conceptually, is going to be proportional to amplitude squared. And we describe amplitude anyways as c sub 0, right? This is an important. In the case of a spring mass, in any case, in a harmonic oscillator, that's proportional to k psi sub 0 squared. We have psi sub 0, which is 4.5, 10 to the minus 2. We have k, which is just obtained. So what's the energy of this vibration? Is going to be 1/2 of k, which is 59 newtons per meter, times psi sub 0, which is 4.5, 10 to the minus 2, and this is squared. And if you calculate this, you're going to obtain that this is about 0.06 joules. So this is just another explanation, another example, about the spring mass system. From the oscillation, from the period and the mass, we can extract the spring constant. This is always going to be a trade-off things. You have mass in the spring, you determine period. You have period and mass, you determine the spring constant. You have spring constant and period, and you can determine the mass. You can play with this as you like, but basically this is the same idea. The period is always the same. Important thing here, the period does not depend on the amplitude. The period does only depend on the mass and on the spring constant. Problem number 4 in discussion says the pendulum makes 28 oscillations in exactly, so it goes 28 cycles per 50 seconds. And the first question that asks is, what is the period? Well, a period is how much time it takes to do one cycle, because it does 28 cycles, takes, 50 seconds to do 28 cycles. Then we have to divide 50 by 28, and so we will find the period, which is going to be slightly less than 2, right? 1.8, 1.9, something like that. 1.8, okay, seconds. That's trivial. Now it's important to see that this is an idea precisely of a frequency. Frequency is how often something happens. So this is happening 28 times in 50 seconds. So another option is just to divide 28 by 50, 28 by 50 is going to give you the frequency, because it's how often it happens. Well, it happens 28 cycles every 50 seconds. And then this will, of course, be in hertz, right? And 28 divided by 5 is going to be about 0.6, maybe, something like that, right? And the idea, anyways, is just going to be like, what is the frequency of a full rotation of Earth? Well, it's going to be, it does one cycle in 24 hours. Or you could you could say it does 3 rotations in 72 hours. How often is the train? If every train comes every hour in a period of 8 hours, you can say it comes 8 times in 8 hours or whatever, right? So this is the idea of frequency, how often it happens. And that's just simply the inverse of the period. The period is telling us one cycle, how long does it take to complete. Now the next question for problem number 4 says, what is the frequency? Well, apparently we just did that, conveniently enough. So that's going to be 20 divided by 50, which is 0.56 hertz. That is the idea. And finally says, what is the length assuming that g is 10 meters per square second, just to make it simple? Well, remember that the idea of a period for the pendulum is going to be given by L divided by g. So in this case, what we're going to do is just trying to solve for L, which is pretty similar to what we've been doing for mass in the case of a spring-like system. And so we're going to have 2 divided by pi squared times g, that's equal to length, right? And so we can replace in here, and the period is going to be 1.8 divided by 2 pi squared times g, that's equal to length. And if we write the numbers, 1 second, let's put directly 10. If we write these numbers, it's about 0.82 meters. Yeah, that sounds right. So as the length, what do you do if you want to increase the period of a pendulum? You need to increase the length. Does the period of the pendulum depend on the amplitude? It does not. There's no psi sub 0 anywhere in here. So let's not force our misunderstandings and our biases onto the physics. We go through the effort of being rigorous precisely to avoid those situations. So if they ask you, 2 children are oscillating and 1 child in the same swing, but one is twice as heavy or as fat, in the case of a human, as the other one. So which one will have a larger period? Both would have the same period. And what if one child goes all the way up and the other one goes slightly less? It doesn't matter. Both will have the same period because there's no amplitude dependency, because there's no mass dependency. The only thing would change the period of a pendulum is if you change the gravitational acceleration, or, which means, for instance, compare Earth to the Moon or to Mars or any other place, and of course the length of the pendulum. Let's see one last example for this chapter. Problem number 5 says there's a fisherman that notices that wave crests pass the bow of his anchor boat every 3 seconds. And so let's say maybe he's in here, and then he's here, and the fisherman is over here, and then there's waves coming, or whatever. And then he sees, maybe let's make a more of a wave kind of thing, with the anchor here somehow. And then we see that the waves are coming to the fisherman or whatever, right? And so he notices that the distance between two crests, it says that the time it takes for that to happen, for the first crest, so the guy goes up, goes down, goes up, and he says, oh, from going up, down, up, it takes 3 seconds. So every 3 seconds he makes a cycle. The other thing he observes is that he measures the distance and he figures out, maybe because there's a friend in another boat or something, and then he figures out that this distance crest to crest is 7 meters. Now what is that distance? That's the distance between a maximum and a maximum in space. And what is that? That's the idea of a wavelength. So wavelength is 7 meters. What is the wavelength? Wavelength is the analogous of period, but instead of working in time, it works in space, because waves propagate in space and time, right? They just travel, and so they travel in space and they take time to travel. That's anyways trivial, but it's convenient to remind, because then we can understand that we're going to have a period, which is how often that thing happens in time. So for a given point in space, how it goes up and down. So for this point in space, it goes up and down, and he says it goes up and down in this time. That is temporal period. But how, if he takes a snapshot now and says, I'm on a peak, what about this? The next peak, where is it found? It's found 7 meters away. And then the next one, 7 meters away. And the next one, 7 meters away, if the wave is periodic, of course. And so what we're going to be saying is that, and harmony, but anyway, those are beyond the point of the scope of this course. So what we're going to see is that the wavelength, which defines spatial period. So how often in space, a maximum or a minimum or a certain configuration, by the way, the configuration we call the phase, right? So minimum and maximum are different phases, the 0 is another phase, anything in between are the phases, and because this is periodic from one to the other, every 360 degrees or every 2 pi will repeat itself, right? It repeats itself, it's periodic. So that we call the phase, the configuration that it is, the particular situation it is. So the distance from 2 points in phase, in the same phase, in the same configuration is what we call the wavelength, and in this case it's 7 meters. And so it's very trivial, because the next thing they're going to ask is going to say, how fast are the waves traveling? And so this is something you could do next time you go sailing. It's precisely this kind of experiment somehow. And then you can see, in this case, or any other case, waves travel at frequency which is going to be equal to lambda. You can figure out this saying, oh, how much it covers in how much time, right? Because, why? We're saying the wavelength is a spatial distribution, and this wave, let's say, is traveling this way. If this guy is at the peak right now, right, this wave is traveling this way, and this is the guy here on the boat. And since I'm on a maximum, how long does it take to go back and down? As the wave travels, the next instant in time, he's going to find himself. So let's make something like this. And so he's going to find himself down, right? And the wave is going to be maybe like this. It's kind of difficult to draw in this case, but the idea here is that as the wave travels, he's going to be going down, right? Because the wave is traveling, so he goes with the wave. It goes down and it's going to go up, but it doesn't move spatially, it just stays in place, right? So how long does it take to go up and down corresponds to how far the next crest is spatially, and that we call lambda. What is velocity? Space over time, right? So how much space you cover in a given time. How much space does the wave cover? Well, the wave covers, goes from this lambda moves here, which is spatially distance lambda, in how much time? Well, it's the time it takes to go up and down, of course, because the guy is going up and down corresponding to the wave. So that's the period. And so from here, it's obvious that the wavelength is going to be frequency, because 1 over t is frequency. So this is the formula for a wave velocity. Any velocity, any wave is going to have a velocity given by this. Okay? So what we're going to observe then in this case is that the velocity of this wave on c is going to be 7 meters, which is the wavelength, times the frequency, which is, it takes 3 seconds for one cycle, so the period is 3 seconds, so frequency is 1/3. So we're gonna say it's 1/3, which is 7/3, which is gonna be 2.3, something like that, okay? 2.3 meters per second. And that's just basically the whole idea of the velocity of a wave. The velocity of the wave is gonna be allowing you to calculate these things. Sometimes, again, we're gonna play with these parameters. You're giving the period and the wavelength, and you're asked the velocity, but sometimes you're giving velocity and period, you're asked for wavelength, you're giving velocity and wavelength, you're asked for period. These parameters are related to each other, so in any case, they're gonna be always, you're gonna be always playing with them. But this definition, again, is very important because the velocity of the wave is the velocity at which the energy is traveling. But that doesn't mean that the guy is oscillating up and down. Well, exactly, that means the guy is oscillating up and down at that velocity. But that doesn't mean the instantaneous velocity of the guy, right? Because the velocity of the guy is just going to be up and down. There's no horizontal component. The wave is traveling horizontal, but this is a transversal wave because the oscillation is happening transversal or perpendicular to the propagation. So the guy is going to have, at this point, he's going to have a zero velocity. An instant later, he's going to have a negative velocity going down. Whenever it reaches this point, it's going to start to observe a velocity going up. So the velocity of the guy is not the same as the velocity of the wave, right? So the velocity of the guy is the velocity of the object vibrating or oscillating, in this case himself, right? So going up and down. But that's not the same as the velocity of the wave. So it's an important thing to bear in mind anyways. Of course, they're going to be related because how often that happens is going to be determined how much velocity needs to gain to actually achieve those. But again, we get into very confusing math probably. So let's just keep it for the time being. Distinguish between the velocity of a given point, how it goes up and down, because again, waves carry energy, they do not carry matter. Therefore, the water is not moving. The water is moving up and down. The water is oscillating, not translating. But the wave is translating because the wave is just the energy translating. It's moving from one point to another. This guy is just moving around the equilibrium position. That's what defines vibration, right? This guy is moving up and down. So the velocity is going to be up and down, simply. But the wave certainly is moving with this velocity, right? Because the wave is traveling in this particular example, right? So this is an important distinction to bear in mind anyways. Velocity of the waves is the result of how fast that energy is being transferred, right? Ultimately, the velocity of and it's going to be related to the velocity of this guy, but the velocity of the vibration itself is just going to be related to how fast the object is oscillating in place, okay? So important thing, from vibration we build waves, okay? So remember always the vibration, a wave is just put a lot of things vibrating and linked together, and that vibration is the one traveling. That's what the wave does. Waves do not carry matter, they only carry energy. Very important idea.